Welcome back, everyone. In this video, we are going to continue learning about molecular polarity. We're going to focus on two main ideas: the importance of molecular polarity, as well as being able to rank molecules based on their polarity. So let's first talk about why you should even care about whether or not a molecule is polar. It turns out that molecular polarity can actually explain a lot of the macroscopic properties of molecules. For example, if you take a bar of soap, soap is made up of molecules that have a polar end and a nonpolar end. The fact that molecule has both polar and nonpolar properties, or excuse me, that soap has nonpolar properties and polar properties, is what allows it to be used as a cleaning agent. The nonpolar regions of the soap molecules bind to the greasy nonpolar regions of fats and oils that are on our skins. And then the polar end of the soap allows it to interact really well with polar water, and which washes it all away. DNA binds together via polar interactions, and it binds tightly enough to keep it stable, but it is weak enough to be able to open up during the replication process. Our foods rely heavily on molecular polarity as well. So substances like mayonnaise are emulsions, and in order for them to be stable, you have to combine in them a molecule called an emulsifier that has both polar and nonpolar properties. So up on the top right-hand corner, you see an image of what mayonnaise would be if it didn't have the emulsifier in it. The emulsifier allows the molecules that have different polarities to interact with each other by interacting with the emulsifier, and that keeps it stable. So a lot of molecular polarity is important because it allows the molecules to interact with other things and perform functions that are useful to us. Let's now talk about ranking molecules in terms of their polarity. This is something that you need to be able to do. So given the following three molecules, try and rank them in terms of increasing polarity. Pause the video and try this on your own. Welcome back. So in order to be able to rank them, we need to first determine whether or not they're polar. We have tellurium hexafluoride, and this is a nonpolar molecule. The reason for this is that even though we have polar bonds for each of our fluorines, they cancel each other out. This cancellation causes the molecule as a whole to be nonpolar. Selenium tetrafluoride, we see it has polar bonds going from selenium to the fluorines, and we have a net dipole moment that goes along this trigonal planar axis. And so this molecule is polar. Xenon difluoride, this we have bond dipoles going from the xenon to the fluorines, but they cancel each other out, making this molecule nonpolar. So how do we rank them? We have two molecules that are equally nonpolar, therefore they have an equal polarity. And the selenium hexafluoride, or excuse me, tetrafluoride is more polar than the other two. All right, let's try one more. We have three molecules. Rank these in terms of increasing polarity as well. Pause the video and try this on your own. Welcome back. So how do we do this? Again, we need to draw the Lewis structures, determine the molecular shapes, and then evaluate the bond dipoles. So we have three molecules, each of which is a tetrahedral electron domain geometry and a tetrahedral molecular geometry. The difference is what the central atom is and what the central atom is bound to. So if we draw in the bond dipoles, we see a very strong bond dipole between the silicon ion, or the silicon and the fluorine. And so its net dipole is very strong, pointing towards the fluorine away from the hydrogen and the silicon. For the middle molecule, we have weaker bond dipoles. The reason for this is because the difference in electronegativity between silicon and bromine is smaller than for silicon to fluorine. And so our resulting net dipole on the molecule is smaller. For the carbon containing molecule, we see that the bond dipoles here are even smaller. And the reason for that is because the difference in electronegativity between carbon and bromine is smaller than for silicon to bromine. And so its resulting molecular dipole is even smaller. So if we want to rank these, we see that the CH2Br2 is the least polar, and the SiH2F2 is the most polar. Thanks for watching this video. That's all for today. Have a wonderful day.